Okay, now I'm going to show you example 6a. Okay, the question is given y equal to ln 1 plus ex. Show that all this, we are going to show two things, and then using the Maclaurin theorem, find the series expansion for ln. Okay, 1 plus ex is ascending power of x until the term in x to the power of 4. Okay, so you see when you have this x to the power of 4 and we are going to use Maclaurin theorem, that means you have to differentiate 4 times until d4y dx4. That's why here you are asked to show d4y dx4 because you want until x power 4. Okay, so now I just want to show you how to do it, how to show. Okay, look at this. Okay, you are given y equal to ln x. Okay, example 6, you are given y equal to ln x. So what we have to do, we differentiate. Okay, we have to differentiate 4 times until d4y dx4. Okay, so when I differentiate dy dx, I just differentiate the ln, I have -1. Then after that, I just differentiate this. That's why I will get ex. Okay, I will get ex. That's why I get this. Okay, so after you get this, we try to see whether I can substitute, I can bring in the y here or not. Because if we can bring in the y here, then it will be much easier rather than you go and differentiate this. Because when you want to differentiate this, it's not easy. Because you want to use u over v, is it? You have to use u over v, the quotient rules. So we just see whether we can bring it up, but here cannot, so cannot. Okay, we just continue to differentiate. Okay, now we do d2y dx square as what I said just now. So this one square, then you differentiate as usual. Okay, the quotient rule, we are using the u over v method, so we differentiate this. Okay, so we differentiate this one square, then this one bring up, then differentiate the top one minus. Okay, this one, then differentiate this. Okay, then we simplify. After we simplify, then you will get this. Now you can see, because if you want to differentiate the third time d3y dx cube, if you still continue to differentiate this, it's quite tedious. It's not easy. So you can see, actually I can bring in the dy dx inside here because this one look more or less the same, isn't it? So if you can change this one to dy dx, then it will be much easier. So you see how are you going to change? You see when I multiply 1 plus ex, then you get this, and then this is exactly our dy dx. So this is much easier to differentiate because you can compare this one with this one. If I want to differentiate the following time, let's say I want to get d3y dx cube, this one is easier to differentiate if you compare to this. That's why the question just guide us to find this first before you keep on differentiate this one, because if you differentiate this one, it will be very long later. Okay, or maybe the power will be, this power will be getting very high. So this is easier to differentiate. That's why the question asks us to show this. Okay, now when I differentiate this here again, I keep this one, then I differentiate this, plus then this one outside, this one waiting outside, this one differentiate, just as I said, go to the toilet, and then you see this one is much easier to differentiate. It's just d2y dx square rather than you go and differentiate this. Okay, so this is your d3y dx cube, and then you simplify, you see d2y dx square, you can bring them together, then after that you will get this. Okay, so I label this as number 4. Okay, so I label on 1 2 3 4 like that. Okay, then I continue to differentiate again, because remember we just have to differentiate 4 times. So this one I just remain here, and then I differentiate d4y dx4. This is what you want to get, and then this one just waiting outside, this one going to the toilet. Here also the same thing, so we differentiate this, and then this one waiting outside, you differentiate this. Then after that we simplify. Okay, when you simplify, okay, d4y dx cube, d4y dx4 here, d3y dx cube, d3y dx cube, this is d2y dx square. Okay, so we bring them together, then we simplify, and then this one we call it as number 5. So okay, finish already. This is our differentiation. We differentiate until d4y dx4 because we want to get until x4. Okay, so next step, what we are going to do, we are going to substitute x equal to 0 into all the equation 1 2 3 4 5 just now. when I substitute x equal to 0, I substitute into equation 1. That is, I put x equal to 0 here. So I get ln equal to 1 plus. This one, E0 is 1. So I get ln 2. That is the first one, or we call it the F0 is ln 2. Okay, so after that, I substitute this one into my dy dx. So dy dx is number 2, that is this one. Dy dx, I substitute here, 0 and 0 here. So this is 1 over 1 plus 1, so it's half. So I will get half. Okay, then after that, I substitute x equal to 0 into d2y dx squared. That is number 3. Okay, number 3 should be here. So I substitute 0, so d2y dx squared. And just now, dy dx, this is half, is it? So I just substitute. I just put in the dy dx is half, so I get 1 over 4. So you just substitute like that. Then after that, you just continue to find your d3y dx cubed. Okay, so you just continue to substitute. This one you substitute into 4, you get this. Okay, because you just look, you can refer back to 1, 2, 3, 4. So you just substitute, you get your d3y dx cubed is 0. And then after that, from number 5 here, you just, from number 5, the previous one, you just substitute x equal to 0 here. So substitute x equal to 0, you will get d4y dx4. So you substitute here. Okay, so once you substitute, you will get d4y dx4 is negative 108. Then you use the Maclaurin theorem. According to Maclaurin theorem, this is the one, f0 plus, because you want to get until x4. So this is our ln 1 plus x. So we substitute all our f0, f prime 1, dy dx, d2y dx squared, or we substitute and then we simplify. This is what we get. Okay, then the last part of the question, what you want to do is this. The last part of the question, we want to deduce the series expansion of ex over 1 plus ex. Okay, so you see, we have got this. Okay, we have got this. This is our series. But now you want to get from here, you want to get ex over 1 plus ex. Actually, what is the relation between this one and this one? There must be a relation. Okay, so you want to get this into this, you just differentiate. You differentiate this one, you will get this. Is it? So that's why, what am I going to do now? I just differentiate. Here, I just differentiate. Because when I differentiate this, I will get this. So when I differentiate the left hand side, I should also differentiate the right hand side. So I differentiate this one, the whole thing. So when I differentiate, then I will get, you see, this is 1 plus ex. I differentiate the ln, I get negative 1. Then I differentiate this one ex, I will get the ex. So I differentiate this one, I get 0, differentiate, I will get all this. Okay, so finally, I will get this one, I will get ex, 1 plus ex, then you get this. Okay, this is what we are going to deduce. So, because you are asked to deduce, that's why you have to differentiate it. That means you can differentiate, or if sometimes they might ask you to integrate. So, if you integrate, you have to integrate all this. Okay, that's all.